Morning students, I welcome you in today's session of physics, and in today's class we are going to discuss interference of light. This is your chapter number 20 of your unit optics. Fine. So we are now discuss about what is interference. So first you can see here, the first one is the principle of superposition, and in your syllabus, as you can see here, what you have to study in your syllabus, first you have to study about the interference, Young double slit experiment and expression for the fringe width, which is your beta, coherent sources sustain interference of light. Fine. So we will start from the principle of superposition. Clear? So as you can see here, this is the definition: when two or more waves travel simultaneously in a medium. Medium means whether it is a air, glass or water, that is called the medium. So what happened? The resultant displacement at each point of the medium at any instant is equal to the vector sum of the displacement produced by two waves separately. Now what does it mean? It says that when two or more waves, suppose you are two waves are traveling in a medium simultaneously. Fine. So the resultant displacement at each point of the medium, so the intensity, or you can say that the displacement produced by the two waves at certain points of the medium at any instant of time is equal to the vector sum of the displacement produced by the two waves separately. Means the intensity displacement produced by the first wave and the displacement produced by the second wave. This is called the principle of superposition. I hope it is clear. It is hold for all types of waves except for the waves of very large amplitude such as laser waves. Fine. So this law holds for every wave, leaving the waves which have a very large amplitude like laser waves. So the principle of superposition means that if the number of waves traveling in a medium, then each wave travel independently as if other waves were not present at all. Fine. The shape and the other characteristics of any wave are not changed due to the presence of other waves. Clear? This is seen in practice when a listener listen to an orchestra, we receive a complex sound due to the superposition of different waves. Clear? Still we can recognize separately the sound of different instruments. Fine. So similarly, our radio antenna is open to the wave of different frequency transmitted simultaneously. As you know very well, there are different types of wave travel in our medium, like radio waves, clear, microwaves, different types of waves, but we are still identify, if we tune in our radio, then there is a different multiple frequencies over there, but still we are able to listen our particular channel. So when we tune the radio to a particular station, we receive the program of that station only if the other station were silent. Fine. So thus the principle of superposition hold not only for mechanical wave but also for electromagnetic wave. I hope it is clear for you what is electromagnetic wave. The wave which do not require any material medium for their propagation, like X-rays. Clear? So X-ray is a electromagnetic waves. Obviously it holds for light waves also. Now we will come to our main topic, which is your interference of light waves. So you can see here, when two light waves of same frequency travel simultaneously in the same direction, fine, then due to the superposition, the resultant intensity of a light at any point in space is different from the sum of intensity of the two waves. Means the resultant intensity of the two waves, when they mix up together or when they superimpose, so that the intensity produced by the light is more as compared to the intensity of the individual lights. So at some point the resultant intensity is maximum, while at some other points it is minimum, nearly darkness. So you can say that the redistribution of light intensity due to the superposition of two waves is called interference. This is the definition of interference. So how you can define it? The redistribution of light intensity due to the superposition of two waves is called interference of light. I hope it is clear. The interference is said to be now when it is said to be constructive and when it is said to be destructive, because there are two types of interference. First one is constructive and the other one is your destructive. So you can see here, The interference is said to be constructive at a point where the resultant intensity is maximum. Clear? When the intensity is maximum, then you can say that there is a constructive interference. And when you call it destructive, when there is an intensity at the point is minimum, or you can say that it is zero, then we called him as a destructive interference. Fine. Now you can see here, this is the Young double slit experiment. Young's produced an experiment for double slit. So you can see here, this is the figure number 1, and in this figure Young described the double slit experiment. This is the important one, so you have to understand it carefully. Now what Young's double slit experiment? Thomas Young in 1801 demonstrated experimentally the interference of light by a double slit. Fine. His arrangement is shown in figure number C, as you can see here in figure number 1. L is a screen. This is the screen you can see here, in which there is a narrow slit. This is the slit. I hope you know very well what is slit. If you mark through a blade on a sheet of paper or a cardboard, fine, so there is a very thin line is created over there, so that is called the slit. So same thing Thomas Young did in his experiment. In front of this screen there is another screen M. You can see here, this is the L screen, and in front of L there is another screen M, which have two slits. This is your S1 and this one is your S2, which carries two slits. S1 and S2 quite close to each other, and you can see here S1 and S2 are quite close to each other. The slit S1 and S2 are symmetrical with respect to the slit S. Fine. And at the same distance from it. Means what it means? It means that the distance of S1 and S2 from the slit S is almost same. Both are at the same distances from the slit. So in front of M there is a third screen N. You can see here in the above figure there is another screen N, this one, at a quite large distance from N. When a monochromatic light, I hope you know what is monochromatic light, light of which is coming from single source or of a single light. Clear? It is known as monochromatic light. Beam is allowed to fall on the slit S alternately. You will get here, you can see here, this is the fringe width, this is the fringes you can get here. So alternately bright and dark bands of equal width and running parallel to the slit S1 and S2 are seen on the screen. Fine. So you can see here, this is the figure number 2, which is showing the fringes which are formed due to the interference pattern over the screen N. So in figure 1, the place of bright band are shown by B, and the place of dark band in the above figure, if you see there is a position of B and D. Clear? It is shown here. This is your D, this is your B. Means B means bright spots and D means dark spots. So that is the thing written here. If you in figure 1 of bright bands are shown by B and the places of dark band by D. So these bands are called fringes. Fine. And this array of fringes is called the interference pattern. So the bright and dark fringes which we will get from the above experiment, they form a pattern that is known as interference pattern, and this is the given here, figure number 2 of the double slit. Now this is the explanation of the formation fringes by wave theory, how the wave theory explain the formation of fringes. So that is the thing we are going to study over here. A cylindrical wavefront starts from the slit S. When this wavefront reaches the screen M, then according to the Huygens principle, the slit S1 and S2 act as a new light source and the secondary wavelets in all direction. Now the light coming from this source S, clear, is a light source for the slit S1 and S2. It is considered to be the new light source for the S1 and S2. Fine. So that is the thing written over here. These wavelets meet each other in the space between the screen M and N. So you can see in the figure 1 are drawn continuous and dotted arcs meet each other in the space between the screen M and dotted arcs with slit S1 and S2 as centers. The continuous arcs represent the crest of the wavelets and the dotted arcs represent the trough. I hope you know the crest and trough. If you see the waves like this, so the maximum displacement in the above direction is known as, this one is your crest, and this is one your trough. Fine. So at place where a crest of one wavelets meet a crest of other or trough of one meet the other, the wavelets are in the same phase. Fine, this is the important line, you have to notice it properly. So hence the resultant amplitude at these places is equal to the sum of amplitude of the two wavelets, and the intensity of light is maximum. Fine. So in the figure, such places are shown by the small circles. If you see the figure number 1 above given here, there are the small circles, black and dark. Fine. The line joining these circles are called antinodal. Clear lines. On the other hand, at place where the crest of the wavelets due to the one slits meet the trough of the wave place is equal to the difference in amplitude of the two wavelets. So if the amplitude of the wavelets are equal, then the resultant amplitude at these places is 0, and hence the intensity of light is also 0. So in the figure, such places are shown by black spots. So you can see the black spots in the figure where the intensity is considered to be 0. Now the line joining these spots are called the nodal lines. Fine, the line joining the black spots is known as nodal lines. You can see here in the figures, nodal and antinodal line. The bright spots joining by those lines are called antinodal, and the line which join the dotted lines, the black spots, are called nodal lines. Fine. Hence the resultant amplitude place is equal to the difference in amplitude of the two wavelets. This is already discussed. The line joining these spots are called the nodal lines. Hence the bright and dark bands are seen alternately on the screen, and in the above figure you can see that since interference is a characteristic property of wave, so interference in light support the wave nature of light. You have to remember what nature interference supports. So it supports the wave nature of light. Now if light of different colors are made to fall on the slit 10 by 10, now in place of monochromatic, if we use the different colors light, then what will happen? Then the bright bands are of the same colors, the width of the bands of different colors are different, then there is a change in the fringe widths. So the interference bands formed by red light are wider than the bands formed by the blue light. Clear? This indicates that the wavelength of red light is larger than the wavelength of blue light. If the slit S is illuminated by a white light, then what happens? The fringe are colored and unequal width. This is the important line, you have to note down this. What happens if the slit is illuminated by the white light? In that case, what happens? The fringes are colored and of frequency or same width, unequal width, sorry. So if one of the slit S1 and S2 is covered, the fringe on the screen disappear. What happens if we covered the one slit? In that case, S1, S2, the fringe on the screen which is formed on the screen N is disappear. It shows that the fringe arises due to the interference of light wave from the two slits. So what is proof from this experiment? That interference is arises due to the superposition of two waves. Now this come to the third one. What are the conditions for constructive and destructive interference of light? We will discuss now this. What are the conditions? So let us suppose here you can see in the figure number 3. In this figure you can easily see that a narrow slit S illuminated by a monochromatic source of light. You can see here this is the narrow slit S. Fine. S1 and S2 are the two similar parallel slits very close to each other and equidistant from S. You can see here S1 and S2 are the two slits and equidistant from S. Suppose the waves from S reach S1 and S2 in the same phase, as if they started from S1 and S2. So let us find the resultant intensity of light at the point P. Here we have to find the resultant intensity. On a screen placed parallel to S1 and S2. Suppose A1 and A2 be the amplitude of the light waves. So from S1 and S2 respectively, the wave arrives at P having traversed different paths. So here you can see they are following the different paths S1P and S2P. Hence they are superposed at point P with a phase difference of phi. This phi is the phase difference. So you can show the relation between the phase difference and the path difference like this. Phi equals to 2 pi by lambda multiplied by x. Clear? Where x is your path difference. Fine. So the path difference is how much? S2P minus S1P. This is your path difference. This one. S2P minus S1P between the waves at P, and lambda is the wavelength of the light. So the displacement at P due to the simple harmonic waves from S1 and S2 may be represented by, this is the simple harmonic equation, y1 equals to a1 sin omega t minus k times of x, and y2 equals to a2 sin omega t minus kx plus phi. Phi is your phase difference, where omega 2 pi is the frequency of each phase. So by the principle of superposition, the resultant displacement at point P is given by y equals to y1 plus y2 from the principle of superposition. So in place of y1 and y2, we put the value from these equations, and finally after solving out, we get here like this expression. Now what we are supposing here, suppose ki a1 plus a2 of cos phi is equals to r cos theta, means this is the term we are supposing that equals to r cos theta, and a2 sin phi, this one, is equals to r sin theta, where r and theta are your new constant. We are considering here the polar coordinates. So in place of a1 plus a2 cos phi, we can write r cos theta. Clear? So this equation changes to like this form: y equals to r sin omega t minus kx cos theta plus r cos omega t minus kx of sin theta. And finally you can you know very well sin a plus b, formula of sin a plus b, which is used in your trigonometry, sin a cos b plus cos a sin b. So same thing we did here, and the equation changes to r sin omega t minus kx plus theta. This is the expression, the second one you can see here. Fine. So this equation is similar to equation 1 and 2 in the above. Hence the resultant displacement at point P due to similar waves of amplitude r. To determine r, we square the equations 3rd and 4th and then add up. Fine. So here you can see this is the equation number 3 and this is your equation number 4. So if we square them and add up them, then finally we get what is r. So r equals to a1 square plus a2 square plus 2 a1 a2 cos phi. This is your resultant intensity at point P. So the intensity is directly proportional to the square of amplitude. Hence the resultant intensity at point P is finally given k times of r square, and in place of r square you can put this value, this one. So finally the intensity at point P comes out like this form, where k is the constant of proportionality, and if I1 and I2 be the separate intensity of the two interfacing waves. So finally you can see here I equals to k times of a1 square plus I2 equals to k times of a2 square. So if you add up both the terms, you get the resultant intensity, which is your I1 plus I2 plus 2 root I1 I2 cos phi. This is the formula for the resultant intensity at point P. So we can say that the resultant intensity at points depend upon the phase difference phi between the two waves at that point. Clear? You can see here cos phi, phi is the phase difference. So that's all for the today's class, student. We will cover up our constructive interference and destructive interference in our upcoming lectures. Till that, do study. Thank you.